I want to introduce quantum fingerprinting. I think it is a cool first example of how quantum states can be used as sketches. A sketch in computer science is a data structure that only supports a limited set of operations. Quantum fingerprints represent bit strings in a way that can pretty much only be used for equality comparisons. Our goal is to map bit strings that are n bits long to some quantum states. We want our map to have the property that for two bit strings x not equal to y, the inner product between the quantum states is small. The property of small inner products will allow us to distinguish the states with high probability, using the swap test, for example, but I will not talk about the details of that in this video. As I've said, we will use these quantum states to compare the bit strings x and y. The reason this is interesting is that psi x and psi y use only O log n qubits, whereas x and y are n bit strings. If you're familiar with it, this is like hashing. We will call psi x the fingerprint of bit string x. Note that if our requirement was that the inner product is exactly 0, then we could only use some orthonormal basis states to encode the bit strings, and this would require n qubits for n bits. So loosening our requirement to having the inner product be small, but not necessarily 0, opens the possibility for a significant space savings. This slide describes how to make quantum fingerprints from a bit string. To start off, choose some large prime p. Make it approximately the size of 100n. The first step in the construction is to define a polynomial P sub x, which is of degree bound n and has the bits of the bit string x as its coefficients. When I say a polynomial is of degree bound n, I mean that it has degree less than n. We also define this polynomial over integers modulo p rather than real numbers. For example, for x equals the bit string 01101, the polynomial we get is z plus z squared plus z to the 4. The second step is to construct a state as follows. This state is an equal superposition of the pairs z and p of x applied to z. Z takes the values from 0 to p minus 1, and p of x applied to z is just the value of the polynomial p of x applied at each of these points. We will now see why the construction from the last slide achieves the requirements stated in the first slide. Firstly, note that when x and y are different, the two polynomials p sub x and p sub y meet at less than n possible values of z. This is because they are degree-bound n polynomials. N points define a degree-bound n polynomial due to polynomial interpolation theorems. For example, 2 points define a line, 3 points define a quadratic equation, and so on. This is the crux of the following proof. We now show that the inner product between two fingerprints is small. The only non-zero terms in the product are those where z1 is equals to z2 and p sub x applied to z1 is equals to p sub y applied to z2. As we discussed, this happens less than n times, and thus the inner product is less than n over p. Since we chose p to be about 100n, the inner product is less than 1 over 100. Note that we could have made the inner product even smaller by choosing p of a different size. For example, p is 1000n or p is 10,000n. The last thing to argue in this analysis is that the fingerprints use log n qubits. Since both registers represent integers in the range from 0 to p minus 1, they each use log p qubits. But since p is approximately 100n, that is also O log n qubits.